Okay, good afternoon. First, a couple of announcements. Monday is a holiday, in case I'm assuming at this point everybody realizes that. And Tuesday follows a Monday schedule. So our next class, which should have been on Monday, is now on a Tuesday. Mondays we have quizzes. So the quiz would be on a Tuesday, but I've decided to postpone it to Wednesday. So there will be a homework assignment, and instead of making the homework assignment due on Sunday or Monday or Tuesday, I'm going to make it due either Wednesday or Thursday. The students have a bit more breathing room. So you can get some work done over the weekend, and you can also hopefully get a chance to relax and maybe chill out a little bit. Okay. So I'll post the dates and everything in the weekly reminder. So again, quiz on Wednesday, not on the Tuesday, and the homework will also be due either on Wednesday or on the Thursday. All right. So let's continue with our most important topic of Thevenin and Norton. All right, equivalent circuits. Thevenin equivalent circuit and Norton equivalent circuit. Did anyone have any questions about the concept of Thevenin or Norton? Anyone? Did you all have a chance to read through the two slides? Any questions before we begin, perhaps? No? All right, let's review. So we have to determine Thevenin and Norton circuit as seen by a particular component. So if the question states, determine the Thevenin circuit seen by the load circuit or the second circuit or RL. Remember, in the random example that I chose, we were using R6, right? We are trying to determine the Thevenin or Norton circuits as seen from the perspective of one particular element. That element could be anything. Element can be a voltage source, could be a current source, could be a resistor, could be a capacitor, could be an inductor, could be a transistor. It could be anything. Seeing from the perspective of a transistor is something that you will encounter like later on in 306, 307, 308, in many other classes. Okay. Seeing it from the perspective of a capacitor or an inductor is something you'll encounter next quarter in EE 211. So again, this is important. The question might state, or it could not state, it would just be obvious. Okay, this is a circuit in front of, there's a voltage source, there's multiple resistors, and you have a capacitor. You should be able to figure out that you need to determine the Thevenin circuit in order to solve for that problem. Okay. So determine the Thevenin Norton circuit as seen by the component X. That component could be anything. You need to remove the component from the circuit, leave behind open terminals. Okay, you have to remove the component from the circuit. It is not part of the analysis. So again, going back to this example, R6 is not part of our analysis. We remove R6 from our analysis. Right, R6 is separate, and you determine everything else. So R6 would be here. Everything else is reduced to a single current source or a voltage source, but R6 is not part of the analysis. So again, remove that component. When you remove a component, it leaves behind open terminals. And I like to refer to them as terminals of analysis. Terminals of analysis. Question? Okay. Is everybody clear on this point? Okay. Now, oftentimes, whether you're, if you're reading a textbook and this topic is being introduced for the first time, then the example problems will simply have a terminal, like terminals like A, B, X, Y, and would simply state, oh, find the Thevenin circuit between A and B. Okay, then you don't have to do anything. You simply begin analysis as it is, right? But if it says determine it from the perspective of a particular component, then you remove that component from your analysis. Now, we need to determine three quantities: Thevenin voltage, Thevenin resistance, and Norton current. Okay. If it just asks Thevenin circuit, then you only need two. If it just asks for Norton equivalent circuit, then you just need a Norton current and Thevenin resistance. But for all intents and purposes, every circuit that that I'm going to bring up is going to require all three. Okay. So Thevenin voltage, Norton current, and the Thevenin resistance. I just refer to this as Thevenin and Norton resistance, but technically it's just Thevenin resistance. I just like to use Thevenin and Norton just to illustrate the same point that the resistance is the same in both circuits. That does not change, right? You find Req between the terminals. That applies to both Thevenin as well as Norton. Doesn't change. Next important point, you're going to redraw the circuit 3 times for each one of those quantities. Meaning you take the original circuit, you redraw it 3 times. And then you analyze the circuit independently of each other. Okay, so let's do a full flow chart. Okay, let's say you're given a circuit. Okay, you're given a circuit. Original circuit. Then, depending on the question, you may or may not have to remove a component, but let's say you do. Remove component. So now you modified it. You have your terminals of analysis. So you have the circuit, you modify, you create 3 different circuits, you analyze it independently. You analyze it independently of each other. Okay. The results you obtain from each independent analysis have no bearing on the other one, because all 3 circuits are going to look very different. Now, when I say very different, they're going to be different. And you will see what I mean when we get to the examples. Okay. Now, obviously, the 3 quantities are related by Ohm's law. VTH times IN. Sorry, VTH is equal to IN times RTH, which means if you know 2 of the 3 quantities, you can calculate the third, right? But it's not always possible to calculate the Thevenin resistance. It may sometimes not be possible to calculate voltage or current because we may have dependent sources in there. And so we need to know how to calculate each of these quantities independently. Okay, so we analyze the circuit 3 times and determine the Thevenin resistance, Thevenin voltage, and the Norton current. I do not absolutely want anyone to use Ohm's law to directly determine any one of those quantities. You can use Ohm's law as part of your analysis. Okay. You can use Ohm's law as part of your analysis, but not as a direct shortcut. Does everybody understand the difference of what I'm trying to say? Okay. All right. You solve this using series parallel analysis, node voltage, mesh current, superposition, any technique that you think would help. Okay. So again, the circuit analysis techniques are not new. We're using the same old circuit analysis techniques that we learned in the earlier chapters 1, 2, and 3. Okay, no difference. We are simply applying those techniques to determine these new quantities. That's all. Okay, analysis techniques are not new. All right, so 3 circuits. How do we determine the 3? Now, how do we set up the circuits? Right, the whole point is setting up the circuits. That's the most important. How do we set up the circuits so we can analyze them? Well, for Thevenin voltage, we don't have to do anything. We have a circuit, we have a terminals of analysis. We simply determine the voltage between those 2 terminals. That is all. So we'd have a circuit, and we have obtained our terminals of analysis. So those terminals are open. If they're open and we measure the voltage, it is known as the open circuit voltage VOC. And that open circuit voltage VOC is the Thevenin voltage. Okay, so VTH is VOC, simply measured at those open terminals. In real life, the measurement, like if this was a procedure in the lab, I don't know. Have you all done this procedure in the lab? Thevenin? Perhaps not. Yeah. In the lab, if you have a procedure, it is as simple as simply taking the 2 terminals and measuring the voltage. That's it, like 5-second job. And then but calculating it is a whole different thing. Okay, so measurement is very straightforward. All right, so now you have your circuit. Simply calculate the voltage at the output terminals, and that would give you your Thevenin voltage. If you short those terminals, if you short those 2 terminals, you now have a short circuit. So if you have a current flowing through that short circuit and you calculate the value of that current, that would give you the short circuit current ISC, and ISC is the Norton current. Okay, ISC is your Norton current. Essentially, remember, again, going back to the example, we have R6, right? So R6 was connected between those terminals. So what we are calculating is what voltage is being applied to R6 and what current would be flowing through R6. Okay. Applied voltage and applied current. That's what we are calculating. So this would, VOC and ISC would be the sources that are being applied to R6. And then finally, we have REQ. Now, REQ is a bit different. If you want to measure the total equivalent resistance between a pair of terminals, then we need to ensure that there are no sources in the circuit. If there's a voltage source or a current source in the circuit, they must be reduced to 0. We cannot measure resistance if there are any active sources in a circuit. They must be reduced to 0, which is something we already learned earlier for superposition. And so that's the only thing. That's the only thing we need to do for modification. Okay. and that would be our Thevenin resistance. So again, calculation-wise, we need to set up the circuit and perform our analyses. But in real life, if you're doing a measurement, it's very straightforward. We simply take your multimeter, measure the resistance between the terminals, that's your Thevenin resistance, measure the voltage, and then measure the current. And that's it, done. All put together, the measurements should not take longer than like 2 minutes. Okay. So how many of you think you can solve a problem for Thevenin voltage and current? Let's look at an example. Any questions before I get to that? Anyone? No? Okay, let's look at an example. Straightforward, it simply asks us to find the Thevenin equivalent resistance between terminals A and B. It does not say from the perspective of R4, or the perspective of any other component. Simply Req between A and B. Okay. So if we wish to measure Req between A and B, we need to reduce all independent sources to 0. Okay. So reducing all independent sources to 0, anyone remember? What do we do with voltage sources? Well, short, yes, but not shorting the source. We replace it with a short circuit. Yeah. And there are some labs that we teach for non-E majors, and one of the things we would get in the habit of those distinguishing between saying short the source or short the terminals where the source was connected. So we replace voltage sources with a short circuit, and we replace current sources with an open circuit. So if we do that, then let's see. All right, let's draw out R1, the resistors first. So we got R1, R3, R2, and then there's a current source here that's left open, obviously. Then there's a voltage source here. We short it out. There's another voltage source here. We short that out. This is B. Another voltage source here. We'll short that out. There's R4. So R1, R3, R2. And then there's another current source at the top, but that is replaced with an open circuit. Okay. So this is where V1 was connected. This is where V2 was connected. I1, I2, and V3. Let's take a pause while you think through this and let me know if you have any questions. Any questions? So what is left behind in the circuit now? Just a bunch of resistors, right? Combine is series parallel, determine REQ. So in this case, REQ is equal to RAB measured between A and B. And what do we obtain? We obtain at the far end, R1 is in parallel with R2, which is in series with R3, which is in parallel with R4. And that's it. It's REQ. This is only possible to calculate if the circuit configuration is in a way that you can reduce it to one single resistance. It may not always be possible to do so. Okay. Make sense? Any questions? Okay. Good. All right. And circuits. As far as circuits go, rather straightforward, not too difficult. Find the Thevenin and Norton equivalent circuits if the 2 ohm resistor represents the load resistance or network 2. In other words, as seen by the 2 ohm resistance. Okay. Determine the Thevenin Norton equivalent circuits from the perspective of the 2 ohm resistance. So that should not be part of our analysis. Okay. Here the terminals are already marked for us. So A and B. So we have A. We have B. It's already marked for us. We don't need to do anything else. But nonetheless, it's not going to be part of our analysis. So set up the circuit to determine RTH. Same thing as previous. RTH. Need to short out. Not short out, but let's do it this way. And then I have 6. So $12 ohm, short, 6 ohms, and 4 ohms. My REQ between A and B. Calculators out and tell me what it is. What do we see at the far end? 12 in parallel with 6 plus 4. 72 divided by 18. What do we have? 8 ohms. Anyone else? 8. All right. 8 ohms it is. 12, 6 are 72. 72 divided by 12 plus 6 is 18. 18 times 4 is 72. So 4 plus 4, 8. Okay. That's your Thevenin resistance. Now, let's look at Thevenin voltage. All right. For Thevenin voltage, we go back to the original circuit. Again, we forget about this. Okay. The value that we obtain for the Thevenin resistance or the circuit that we use for Thevenin resistance has no bearing whatsoever on the circuit we use for VTH. Be absolutely clear about this again. We are redrawing that circuit. Okay. If you want to find Thevenin voltage and Norton current, we need to have a source in there. The circuit for Thevenin resistance does not have a source. Okay. So forget about that circuit. We go back to the original and redraw that circuit again. And so what do we have? We have make my job a bit easier. And so now this source comes back and we have a voltage source of plus minus 30. Okay, plus minus 30 volts. Terminals of analysis remain the same, A and B. But instead of REQ, now we're measuring the open circuit voltage between the two terminals. The polarity that I'm showing in there is an assumption. Okay, you can assume the opposite polarity, it doesn't really matter. But the polarity that you choose for the Thevenin voltage must match the current direction that you then assume for the Norton current. So if I choose plus at the top and minus at the bottom for my VOC, my Norton current should be going from the top to the bottom, so downward direction. If I choose minus at the top, then my current should be flowing upwards. Again, the polarity that you choose is immaterial. It does not matter. The answer at the end would reflect. It would either be plus or it be minus. Okay. So if you choose, if one student chooses this polarity and another student chooses like minus and plus, one student might obtain plus 5 volts, the other one obtain minus 5 volts. Both answers are correct. So just let you know, polarity does not always have to be what I'm drawing in here. Okay, what do you think the circuit is? Well, I'll tell you, the circuit is a voltage divider. But now you think on it and tell me whether you understand it's a voltage divider. Again, the same concept, right? We have current coming from the source going in this direction through the 12 ohm resistor. When it reaches this intersection right here at the top, some of it would go down the 6 ohm resistor, some of it will go to the 4 ohm resistor. However, the 4 ohm resistor is open. Because it's open, there is no pathway for the current to take, right? And if it's no pathway for the current to take, that means there is no voltage drop across that 4 ohm resistor. If there is no voltage drop, it means both ends of the resistor are at the exact same potential. And because both ends of the resistor are measured with respect to terminal B, the voltage at A and B is the same as the voltage here. So there are only two resistors in the circuit, the 12 and the 6 ohm. And so I can draw the circuit like this. So you have 30 ohms. Sorry, 30 volts. Oh, this shouldn't be like this. Should be like this. But because it's open circuit, it may as well not exist at all. So this is 12, this is 6, this is VOC. You can write VTH is equal to VOC is equal to a fraction of 30 volts and apply voltage division. So 6 divided by 12 plus 6 should be 10 volts. 12 plus 6 is 18, divided into 3 equal parts. 6 plus 6 plus 6. So 30 volts divided in 3 equal parts, 2:1 drop. The series connection of resistors is in a ratio of 2:1. Okay. Did that make sense to everyone? Okay. All right, then let's look at Norton current, and I'm going to go to the left. Okay. Let's draw a line right there. And okay. Circuit for Norton current. Again, we redraw the circuit, and I would obtain current needs a pathway to flow through. So we need to short the output terminals. Terminals of analysis are are joined together in order for current to flow through. So you have current flowing, and because I chose the polarity as plus at the top and minus at the bottom, my current flows from top to bottom. So ISC is flowing in the downward direction. Okay, let's take a pause while you look at the circuit and see what that short circuit does. What does it do? What does it do to the 4 ohm resistor? Anyone? It does give a pathway to the current, but more importantly, it's taking the 4 ohm resistor and it's connecting it to the other end of the 6 ohm resistor. So what is the relationship between the 4 and the 6? They become in parallel. Absolutely. Both of you are correct. The 4 and the 6 ohm resistor are now in parallel. We want to determine the short circuit current, ISC. But because it's shortened, if you take the pathway and you extend it backwards, what else can we say about this short circuit current? It is the current that is flowing through the 4 ohm resistor. It is the current that is flowing through the 4 ohm resistor. So we can use multiple different techniques to determine this current. We can first find REQ, complete and total REQ for the 12, 6, and 4 ohms, and then determine the voltage across the 6 and 4 ohm resistors in parallel. Apply voltage division directly or apply current division. Either ways, as practice, I would strongly suggest or recommend to students that you use all available techniques just as practice, because you would know what the answer is. So you can use all available techniques to find the same quantity in multiple different ways. Okay, so let me redraw the circuit in this manner. So plus minus 30 volts. I have this resistor here. Okay. A and B are here. This is A and this is B. All became one single node, obviously. So this is 12 ohms. This is 6 ohms. And this is 4 ohms. The voltage across these two is obviously the same. I'm going to call this voltage as Vx for convenience. Vx. Total current is coming from the supply, is going down here, causes a voltage drop across the 12 ohm resistor. Let's just label it, I don't know, and do it later. 30 volts. So two options. I can combine 6 and 4 together, find the voltage Vx, right? Or I could find total current coming from the source and apply current division. Let's just do voltage first. Six and 4 in parallel will give me a resistor of 6 4s are 24 divided by 6 plus 4 is 10. So 2.4 ohms. So 6 and 4 in parallel is 2.4 ohms. Vx is a fraction of 30 volts. A fraction is given by 2.4. Somebody perform this calculation, please. $16.6. Anyone? Is it 16.666667? That's a big, it's a big difference. 16.667. Is that what, anyone else? Just as a side note, sometimes when you have decimal places, we are working with large resistances. Resistances could be sometimes in kilo ohms or mega ohms. And so then it does affect the circuit larger. So I always advise students to take like 3, 4 decimal places and then round up at the very end. Anyway, so Vx is 16.667 volts. So therefore, what is my ISC? Oh, that's right. Sorry. So 2.4 divided by 14.4. Oh, current is 0.1667. So what is this voltage? Okay. Oh, so the final answer for ISC is pi divided by 4. Let's check, which is where we use the Ohm's law at the end. So use Ohm's law to verify. IN times RTH What is my RTH? Eight ohms. It gives me 10. And that's VTH. So verified. You can also see the downside of using Ohm's law to find a quantity directly. Let's say your calculation for RTH was incorrect, perhaps, or VTH was incorrect, right? So if we don't determine Norton current and we take the incorrect value for RTH or VTH and we apply Ohm's law, well, now instead of one incorrect value, we have two incorrect answers. Make sense? And that's why we use Ohm's law at the very end for verification. We can use it for analysis during the problem, but we cannot, or we should not be using it to directly determine the values for any of those quantities. All right, questions? As far as analysis goes, this was rather straightforward analysis. The analysis is not important. What is important, I'll strongly urge again, I'll strongly emphasize the point again. What is most important is understanding and setting up the correct circuit. Okay. Setting up the circuit is the most important for Thevenin and Norton. It is not the analysis. The analysis techniques are separate. So there is no actual new analysis technique that we are learning. Again, wish to emphasize that. We learned about series and parallel resistances, Ohm's law, KCL, KVL, node voltage analysis, mesh current analysis. All of those techniques are the same. We can pick and choose any one of those according to what we think fits the best. For the Thevenin and Norton, the most important point is setting up the correct circuit. If the setup of your circuit is incorrect, then the analysis does not matter after that. So setting up the circuit is the most important. So again, let's take a pause, think over all of this. Let me know if you have any questions about anything. No questions? Okay, we'll end class here today. We'll pick up here again on Tuesday with the second example, and then we'll again solve a few more. I'll post the homework and then also go over the homework problems in class on Tuesday. And then quiz on Wednesday will be about mesh current analysis. Okay, mesh current analysis. All right, have a good weekend. Again, work a little bit, get caught up on work. That's what I plan to do. If you have any questions, reach out to me. I will be available over email, Zoom if need be. But again, take some time to chill and relax if you can. All right. Enjoy your weekend.